The table gives the number of passenger cars C in millions in the U.S. in the year T. So here are my questions. I have the table listed every time so that we can take a look at the table closely as we go. Do f prime of t and f double prime of t appear to be positive or negative during the year 1940 to 1980? Now they ask you that specifically because the data does get a little wonky past 1980. So I look at my function. It looks like as my time increases at equal distance, my number of cars, passenger cars increases. So that means that f prime of t has to be positive. Whenever my original function is increasing, my derivative is positive. Same thing with f double prime. Whenever my derivative is increasing, my second derivative is positive. So it's the same pattern all the way up. Now I have to kind of look at what the second or the first derivative, how it's behaving to determine the sign of f double prime. So all I'm going to do is just take the difference between these numbers and see if it's increasing or decreasing. It's kind of a real rough estimate of the derivative. So the difference between 40.3 and 27.5 is 12.8. The difference between 61.7 and 40.3, 21.4. The difference between 89.2 and 61.7, 27.5. The difference between 121.6 and 89.2 is 32.4. So you can see my function is increasing and the rate is increasing. So that means f double prime of t can be estimated as being positive. It appears that way. Now part B says, using a central difference quotient, estimate f prime of 1975. So if I write down what f prime of 1975 is using the difference quotient, that's going to be an approximation of f of now two numbers surrounding 1975, 1980, and 1970. So that's going to be f of 1980 minus f of 1970 divided by 1980 minus 1970. Notice that these numbers that are input here are the same numbers that are down below. So if I keep doing the math, f of 1980 is 121.6. F of 1970 is 89.2. And the difference between these 2 years is 10 years. So if I put this in my calculator, the calculator is over here. 121.6 minus 89.2 divided by 10 gives me 3.24. So what does 3.24 mean? Because we need to use units, interpret the answer in terms of passenger cars. So the units of measure, in this case, the rate of change, we can think of it as the change in C with respect to T. So that helps us a lot with our units of measure. So the units of measure, the change in C is the change in millions of cars. And the change in T is years. So the units of measure is millions of cars per year. So I wanted to write a sentence in 1975, the rate, which is this number, at which the number of passenger cars was increasing is 3.24 million cars per year. Okay. Now let's keep going. The last guy down here, I need to use a central difference quotient to now estimate f double prime of 1975. And then I have to interpret that. So f double prime of 1975 is equal to, now 1975 falls between these 2 years, f prime of 1980. Because remember, the second derivative is the change in the rate of change. And f prime is my rate of change. So f prime of 1980 minus f prime of 1970, all divided by 1980 minus 1970. So now in order to do this, I have to come off to the side and write down what f prime of 1980 is and what f prime of 1970 is, just like I did in part B. 1980 is right here, so I want to use f of 1990 minus f of 1970 divided by 1990 minus 1970. Now this is just like the previous problem. F of 1990 is 133.7. F of 1970 is 89.2. And the difference between these two is 20. So I do this math. 133.7 minus 89.2 divided by 20. 2.225. Do the same thing for 1970. So 1970 is right here. I'm going to use the two numbers on both sides to make it a central difference quotient. It weirdly enough is the most accurate. So this is going to be f of 1980 minus f of 1960 divided by 20. And that's going to be, I guess really this 20 should be 1980. Let's not skip too many steps. Minus 1960. F of 1980 is 121.6. F of 1960 is minus 61.7. And now that's all divided by 20. Sorry. Don't always look up all the time. So 121.6 minus 61.7 divided by 20 gives me 2.995. All right, now I'm going to take these two numbers and I'm going to return them back in here and see what I get. So I'm going to approximate f double prime of 1975 using these two approximations. So 1980 is 2.225, 1970 is 2.995 divided by 10. So let's see what that number turns out to be. 2.225 minus 2.995 divided by 10. Negative 0.077. No, it shouldn't be. Yeah, that's right. Did I type that all in right? Negative 0.077. Okay. You're not careful, man. You can get these numbers confused really easy. All right, so what's the unit of measure on this guy? It's going to be millions of cars per year per year. So notice my second derivative is negative, and in part A, I said something about the second derivative looks like it's positive, but something happened in this problem with the wonky numbers. So these numbers over here, actually, the rate starts decreasing right around this time, and these numbers, 1990, are involved. 1980, 1990 are involved in coming up with this rate. So that's why the rate is negative in 1975, because we're using numbers that are a little off. But nevertheless, basically this is saying in 1975, the rate of change is decreasing. So in 1975, the rate is decreasing. EAS is decreasing, and the number of cars being sold, and how can I say, 1975, the rate is decreasing, and the rate of number of cars sold no, I guess not the rate. This is really hard to do. In 1975, the rate is decreasing, and the number of cars sold is slowing down. There we go. You have to think about it. So you have to think the rate is decreasing, but how does that account for the actual number of cars? So the rate is decreasing, that's this number. Therefore, the rate of the number of cars, not the rate, the number of cars sold is slowing down. So it's the idea of it's increasing at a decreasing rate, so it's slowing down like that. Wow, that's a tough problem.